Ladies and gentlemen, welcome back from spring break. This is the final lecture file I have for content material before we start getting into review work. We're so close to the end of this unit, I want to go ahead and finish it off. So we're looking at induction and how we're going to apply it to circuits. And there's a few equations I've got for you here. This one I don't think I quite got to on the previous lecture file. And we're not going to spend a lot of time on this one. It's really just showing the relationship between magnetic and electric fields. For more details on this, go anywhere on the internet and look up Maxwell's equations, and you'll see a lot more details. But the idea here is, up here we're looking at, remember you had your change in flux over time, gave you your EMF. So we can look at the integral of our electric field with relation to that dl. We're thinking about the V equals ed for a parallel plate. So your voltage equals electric field times that distance between the plates. That's where this came from, or where this started, I should say. But the V equals ed came from this, and we got our KQ over R from this as well. So integrating our electric field equation and getting voltage. This is your general equation here. These dots are a little out of location. Those should be a little bit lower. Those are dot products. All right, giving you scalar answers. So your changing magnetic field gives you an electric field, and if an electric field is growing in a capacitor, it's going to create a magnetic field. So the two are definitely related. Which takes me to this page. Accept my official apology. For the next 6 pages, you will find nothing but derivations of a few formulas. They will not excite you. You will find them boring. Those with effects are weird, and at the end you will find dun 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 the final formulas that I have for you. This is it. We're down to the wire. Stick with me. We're going to make this work. Okay, so in a previous lecture I mentioned that if you had an inductor in a circuit, and the idea was if you flip the switch, then it's going to start putting current through your circuit. The current will go into that inductor, which is a coil, which is going to create that magnetic field in the coil. But it's going to resist what you're doing. So it will have this blossoming magnetic field inside the coil. That blossoming magnetic field will then induce current in the coil, going the opposite direction, resisting change. And this is called back EMF. Back EMF, remember EMF is electromotive force or voltage. It's simply voltage the other way. So your inductor becomes I don't want to say voltage supply, but it does create a voltage the opposite direction, trying to resist that flow of electricity. So it becomes a voltage drop, like a resistor is a voltage drop. So you've got an equation there, N phi equals Li. L is the inductance of the inductor. I is the current. So inductance is, N is that number of coils. Your phi is your flux divided by I, so your flux is basically BA. Your inductance is NBA over I. If we figure out our numbers for a solenoid and put those in there, remember the magnetic field in the solenoid, put our bunny formula in there, and we end up with the inductance of a coil is mu naught. There's that permeability of free space. Inside it, there's n squared, number of coils squared. Notice it's not coils per, well, it is coils per length. Notice you got it over L over there. So it's coils per length with your n over L, but you're timing n again. So we can't use the little n in this equation because we need the big N anyway. So we may as well keep the big N in there. So the number of coils does matter, not just the coil density. And then that A is that cross-sectional area of your solenoid, not of the wire. So if we're looking in the hole of the solenoid, that A is the area of it. So the size for the solenoid does matter for the inductance of it. Bigger the solenoid, bigger the inductance. And now notice that's just the physical characteristics of the inductor. Take an inductor off the assembly line. How big is it? There's your A, there's your L. How many coils does it have? There's your N. And is it empty? If it's empty, you've got your mu naught. If you had an iron core in there, which is probably what you'd end up doing, your mu naught would be times the relative permeability of the iron. So times 500, 400, 600, something like that. So that L is just a value. That gives us the inductance of a coil, which we can use for our energy calculations and other formulas. All right, so that's the physical inductance of an inductor. All right. So if we said, hey, here's our 300-turn inductor, it's 3 centimeters long, cross-sectional area 0.5 square centimeters. What's the inductance? It's air-filled. What's the inductance if it's got an iron core inside? We basically just plug and chug into the equation. So we plug and chug into that equation for that, and you get 1.89 times 10 to the minus 4. This is just a plug and chug equation. I'm not worried about quizzing you on this one right here. And it's hertz. No, sorry, take it back. My apologies. Hertz is frequency. H is henries. So inductance is measured in henries. If we put an iron core in there, since our mu naught becomes mu naught times 400, it's 400 times bigger, and we end up with more henries. All right. So here's what we're going to play with. This is where actually they're kind of fun. I like inductors in a circuit. So we've got our equations on the left. There's your back EMF. There's your inductance of the coil. So there's just a collection of equations we've got. On the right-hand side, we set up our Kirchhoff's loop. We've got, remember, sum of the voltages equals 0. So say you've got a battery giving us a voltage of V. You've got your voltage, or your back EMF. That L was inductance. Di over dt, change in current or change in time, just like we had with capacitors. And then plus that IR. If I had done this properly with the Kirchhoff's loop, it would have been 0 equals V minus IR minus LDI over dt. That's why there's a minus sign here, is because it's the voltage drop from the inductor. When you rearrange it and solve for V, you get your voltage drops on the right equals your voltage increase on the left. If there was no resistor in the circuit, we would just get this. But typically you're going to have a resistor in there, which is why it's called an RL circuit, just like that capacitor had an RC circuit. So here's your voltage drop for the resistor. Remember, it's going to be IR, whatever that current is, times resistance. But you have to have a change in current to have a back EMF for the coil. Once you hit a steady state, meaning it's been running for a little while, and now you've got current going through the coil, the magnetic field is in that coil, the magnetic field isn't changing anymore, it's a constant magnetic field. Constant magnetic field is not generating current in the wire, therefore there's no back EMF, therefore a solenoid is just a coil of wire, it's just a wire, and it has no notable resistance. So we just have V equals IR. Hey, look, Ohm's law, because you've got a wire, inductor is just a wire, and you've got a resistor in the circuit. So you have to have a changing current. So that means you're only going to have this back EMF for a short time when you throw that switch. Yes, there's a time constant for inductors, but we don't play with it much here. Once you have the, actually let me pause this for a second, catch my breath. Okay, I did tell you a few minutes ago it was just going to be a series of equations, so here's your series of equations. So remember when we charged a capacitor, you charge it up, you had a certain amount of charge on it, you had a certain voltage across it, certain capacitance, we had energy in the capacitor. If we hooked that capacitor up to a light bulb, it would light the light bulb for a short time, and that energy would dissipate in that light bulb. Well, from those equations, we can rearrange some stuff and get energy per unit volume of an electric field. Great, we're not going to use that for anything except plug it into the next equations. And when we do, there's a derivation in your book. It comes up with that second to the bottom line. Potential energy of inductor is 1/2 Li squared. Notice that 1/2 something something squared seems pretty common for energy. So what that means is, once you've got that current going through the inductor, and it's a steady state, and you have a magnetic field in the inductor, it has energy. It's just current going through the wire, so the energy is not stored in the form of current. The energy is stored in the form of that magnetic field that is in the inductor. Remember, it's a solenoid. So we've created this magnetic field. It's pretty strong. It's inside the solenoid, and it's there as long as that current is running. If we were to throw the switch and no longer provide current to that inductor and no longer provide current to create that magnetic field, the magnetic field would collapse. As that magnetic field collapses, think about that for a second. As the magnetic field collapses, it's a changing magnetic field, a changing flux, which will generate a current. And it will generate a current in the direction the current was already going, because it's trying to maintain the status quo, trying to keep things the way they are, meaning it's going to keep providing current to your circuit as that magnetic field collapses. How much energy can it provide? There's your formula right there, the 1/2 Li squared. So if we had a light bulb hooked up to it and we close and we open the switch for the circuit so the battery is no longer providing electricity to that light bulb, the inductor will provide the electricity to that light bulb, trying to push that current through it and keep that light bulb lit. It won't last for long, but the idea is that if we then threw the switch back on again, maybe we'd never notice that the switch was open briefly. So that's that whole power balance conditioning, line conditioning, where you're trying to get a circuit to ignore spikes in energy or slight drops in energy, and the inductor keeps it going or prevents it from spiking. So that's the energy stored in that inductor. There's also energy of a magnetic field, which is the bottom equation, which is your magnetic field squared divided by mu naught. So I don't think I've seen that equation ever show up on an AP test, but hey, it could be wrong, I just never noticed it. But the second to the bottom equation, that one, is typically your, hey, here's your energy equation. All right, energy of a capacitor, inductor, sorry. All right, common examples of induction. We've seen one similar to this. Let me reset this for a second. I'm saving the audio segments in chunks. That way, it's just easier for the software to import and export. Okay, so here we have a constant magnetic field. We already dealt with changing magnetic fields earlier with the change in flux over change in time. Remember that? But here we don't have a changing magnetic field, we have a constant magnetic field. But we have a coil of wire. So here we have a coil of wire, and we're going to take this wire and put it in the magnetic field. Now remember, if the wire is just sitting in the magnetic field, then there's no change in flux, there's no wires moving through the magnetic field lines, there's no current induced. If we start to move it, however, now we could potentially be creating current. Now think about what happens if I move this straight to the right. Look at the wires on the right over here. Use right-hand rule. The velocity is to the right, so hold the thumb to the right. Field is out of the paper, or out of the page toward you, so there'd be a downward force on the charges inside, making current go down. Problem is, over on this side, same thing over here as it goes to the right. You still have velocity to the right, thumb to the right, fingers towards you for the magnetic field towards you, and you still have down, so you still have current pushed downward. So the left side and the right side both push current down, which means they fight each other, and you get no net current. The wires down on the bottom and top are not crossing field lines, so there's no current on them. So you end up with no current if you just wiggle it around inside the magnetic field. If you think about it as the change in flux over change in time here, well, there is no change in flux because the amount of magnetic field inside that rectangle is unchanging. It's the same quantity of magnetic field at all times. So that's the other reason we can say, hey, my average EMF is 0 because my change in flux is 0. And now let's move it so it's not inside. So now the left-hand wire is not in the magnetic field, but only the right-hand side is. Now as we move it to the right, our flux is changing. Here we have very little flux. There's only one row of magnetic field lines. Now we have twice as many, 3 times as many. We're getting more and more and more magnetic field going through the rectangle, more flux. So we do have a change in flux. Now, it's hard to do this without the smartboard, so I'm going to try and do it verbally and let you kind of write it on paper and look at it yourself. You've got your change in flux being that area. The area is changing. The area is changing. Remember, I'm only talking about the overlap area, so the amount of dots inside the rectangle here. That area is changing at a rate of change in this bottom distance here, right? Very small distance, now it's a big distance. So my change in distance over time. What's my change in distance? Change in distance over change in time, that's velocity. So my change in flux becomes my velocity of this movement. Now it was change in area, which is this distance times this distance. This distance doesn't change, that's just my L. So I've got my velocity times L. Hey, look, velocity times L. And that is the V is my change in the X over time. L is my unchanging Y. So there's my X times Y, there's area. Area times B is flux. So my flux over time is this. So really, these are the same equation when done this way. And you may have to write that out and see that conversion. Remember, this change in flux is change in area. Change in area is my change in X times my Y. Change in X over T. Hey, there's my over T. So change in X over T is V. My L is still there. Times B is the other part of that flux variable. So we end up with the velocity of this wire on the right, this piece right here. Velocity of this wire times the length of this wire, hey, VL. It gives me my EMF. So I get the same EMF whether I'm using my change in flux or my VBL. They're both valid. They give the same equation. Okay, now this brings up an example that I always thought was kind of strange. So, we always talk about the flux where you have the magnetic field going through the loop. We also talk about things like the wire moves through the magnetic field lines, and if the wire moves parallel to the magnetic field lines, then no current is induced, which implies that the wires in the field have to touch. So look at this example. You got a magnetic field sitting in the screen, and you have a loop of wire on the screen. Notice they don't technically touch. Really strong magnetic field there, but the wire's bigger than that. As it turns out, if that magnetic field were to fluctuate, it would still be a change in flux inside the loop. Therefore, it would still induce a current, even though it doesn't look like the field and the wire touch each other. And that always struck me as kind of strange. But think about it this way. Remember, magnetic fields are closed loops. So every field line's a closed loop. So picture those dots on the screen. Those are the magnetic field lines coming out of the screen at you. Those will come out towards you, and then they're going to loop around in a big circle and go all the way around, and then end up somewhere behind the board and then come back at you again. So every loop, or every magnetic field line, is a loop. So while technically the magnetic field and the wires are not quote-unquote touching, if that magnetic field were to fluctuate, meaning it gets stronger and weaker, then that magnetic field line that comes out of the page loops all the way around, probably outside the loop, and then goes back into the, comes back at us again for a second time. As that field gets bigger and stronger, that relationship is going to change. So picture that field collapsing. Those magnetic field lines that technically we can say aren't touching the wire are going to collapse, and as they do so, they're going to brush against the wire. They're going to cross that wire as it gets smaller. Likewise, if the field got stronger, then as that magnetic field blossoms outward, then those field lines will brush or cross the wire as they get bigger. So yes, visually, the field and the wire are not touching, but because the magnetic field is much bigger than what we actually see here, that large bubble of a magnetic field does encompass the wire. We'll say that, what's the biggest thing on planet Earth? The biggest thing on planet Earth is the magnetic field, because the magnetic field is much, 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 much bigger than planet Earth. So same kind of thing here. We're seeing a magnetic field that is smaller than that loop of wire, but when you take the actual magnetic field into account, it's really spread out thinly in a huge bubble area. Technically, it is bigger. So when we talk about our flux being our magnetic field times the area times cosine of theta, there's your top of the screen there, flux equals. All right, that is the area of the smaller object. So in this case, since the magnetic field area is smaller than the wire area, our A would be this A right here, whatever this area would be defined as being. Whereas if we made the wire smaller, let me unlock that. If we're to make our wire smaller and say, hey, this is our loop of wire that we're having a current induced in, then our A would be the area of the metal wire loop. So it's always the smaller of the two, because all this magnetic field out here is not affecting our coil. So when you get your flux calculation, flux is BA cosine theta, A is the smaller area of the two, and even though it doesn't look like they're touching, the field is much bigger than what we see. This is just that focused area that we're using for our calculation for flux. And then, of course, we're going to get our actual EMF is going to be the change in flux over change in time. So if we had a function for magnetic field or function for area, we could put that in there and do the derivative. If we just said, hey, we have an initial area or an initial field and then a final value, we can take the change in and get the average EMF. Remembering to multiply by n, which is the number of wires, coils in our coil here. Note, area is always that smaller area. Okay? Always struck that as one of the strange things. Here's the part I find fun. So we're looking at a circuit, and remember we did capacitor in a circuit, capacitor, resistor circuits. We had to deal with what voltage does the capacitor see. Same exact thing here. If this were allowed to go for a long time, then the capacitor right here would end up just being a wire. So it's just a wire. It's a short circuit across the 30 ohm. So no current goes through the 30 ohm. It all goes through the coil, which means your current would go through the switch, through the 20 ohm, only through this wire and back to the battery. So you do Ohm's law of equals IR with a 10-volt battery and a 20 ohm resistor. When we first turn on the circuit, however, first close the switch, this inductor right here is going to start forming a magnetic field. Remember, this is a solenoid. So as that magnetic field grows and gets stronger, you have a changing flux inside a wire. That changing flux inside the wire will create that back EMF and give us resistance, initially a lot of resistance. So that means all the current will go through the 30 ohm because it's acting like an open initially. So we throw the switch, we have current go through the 20, goes through the 30, nothing goes through the inductor at first, and we have our total resistance being 50 ohms. But as time goes on, this magnetic field will get to its maximum value, and once it's at its maximum value, the magnetic field is no longer changing, flux is no longer changing, current is no longer being induced, now it's just a wire, and now it's that 20 ohm resistor is the only resistor we worry about. That would look like this, I believe, on a circuit. See if I have the right one set up. Okay, so there's our system. There's no current flowing. So watch what happens to the current when I throw the switch. Initially, nothing went through the inductor, it all went through the resistor. But over time, the inductor is just a wire. Now nothing goes through the resistor, and it all goes through this. And you see down here, you see your current changing. And over here you have your voltage changing, voltage across the inductor. Since the inductor is just a wire, that voltage is really going down to nothing. It's 1 millivolt. It's approaching 0, or microvolts, etc. And the current is going to the maximum current, which is all the current going through this guy. Okay, so that's what that circuit would look like on that simulator. The next one shows a switch setup here. Notice it is nice steady state current going through. The amount of current going through the inductor is 35.7 milliamps. When we throw the switch, it wants to maintain the status quo. As the magnetic field collapses, it will induce a current in the same direction, which means it'll keep that current going downward briefly. And then it slows down, stops because it isn't a power supply. There's no chemical reaction going on like a battery. Eventually, that energy will go away. Remember that earlier energy calculation? And that energy will all be dissipated as heat in the resistor. And once that quantity of energy is gone, yeah, there's no current being induced. Put this back up. Notice it took a little while for that current to build up speed. And keeps going briefly and then slows down and stops. And these links you see right here would actually go to those simulators. I highly suggest you go play with those. The third one has a capacitor. I don't think they would ever do this, but I thought it was fun because notice in this right-hand circuit, there's no resistor. None. which means there's no resistor to dissipate the heat, to dissipate the energy. Obviously, in a real-world situation, the wire would end up being the resistor, and the wire would heat up, and the wire would act as our resistor of 0.001 ohms or something stupid like that. And eventually, the wire would get hot enough, absorb all the energy, and the circuit would die. But because I believe in this online simulator, the wires are perfect, there is no resistance, which means the current wants, or the inductor wants the current to keep going once I throw the switch. So think about this for a second. Pause the video, make a prediction. What's going to happen? The inductor wants to keep the current going. It'll keep pushing the current going, but with that switch switched over, it's going to go this way. So the current's going to go toward the capacitor that starts out like a wire, but ends up like a open. Pause, check it. Okay, let's see what you if you got it right. So the inductor pushes the current, which pushes charges onto that capacitor, which literally charges the capacitor. Once that capacitor is charged, though, now remember, it has a voltage. It now acts like a voltage supply, and it sees a circuit, so it tries to push current through the wire. But the inductor resists it until the magnetic field is there, in which case, hey, look, you have a magnetic field. But now you've discharged your capacitor, and now you have a you have an inductor that has current in it, and it keeps the current going. And it fluctuates, and you get this infinite system where it keeps charging and discharging the capacitor, first one way and then the other. Think of it as the inertia. But yeah, you would never have a real circuit like this, and it would dissipate because the resistor, the wire, would be your resistor. So it just amused me when I found out that's what would happen. I was experimenting and came up with this and went, huh, cool. We got the prediction right. It's a tough prediction. We go back over here, then it's just going to go back to that steady state once we finally get that magnetic field set. All right. So go ahead and try and solve these problems. After you've done it, pause, solve. You have now unpaused. Seriously, guys, give it a shot. The web assigns are going to be due. You can still do the web assigns. I know this won't be on the AP test, but those of you who are going to college, who are going to see this kind of stuff in the future, I've gotten so many emails from students who have said, hey, Mr. Medic, AP really set me up for these college classes. Yes, I'm taking these courses. A lot of the stuff looks familiar. I'm walking through it. I'm having a great time. It's easy. And the students around me, some took AP, some did not take AP. And regardless, they're struggling. Our AP program is thorough, and this is part of the thoroughness of it. So give it a shot, even if it's not going to be on this year's AP test. If you're taking any physics in college next year, you may well run across it again. So at least it'll be familiar in the back of those brain cells. That's it. No more smortboard files. Is it possible? Is the interview that close? No, not really. We're a little ahead of schedule. So, but everything's messed up. So it's going to be a review from this point forward. So we're doing lots of review discussion, and I got to figure out how I'm going to do some of the stuff with you. So I want you guys as prepped as possible for your upcoming online AP tests. I'll check the timing on the web assignment. This video, I don't know how long the total video is, but I will look at the length of this video. I'll look at the two web assignments that are coming due. I'm probably going to pull them forward a little bit. And these assignments will be, let's see, this is Tuesday. So probably Tuesday's assignment completely, maybe all of Wednesday. So I may not have another assignment for you until Thursday. Obviously, I'll put an assignment for Wednesday, saying what Wednesday is, but it'll probably be the web assigns. I'll check that. And that means Thursday, if my prediction is right, we'll be starting reviewing stuff Thursday. There is no school on Friday. I will not have an assignment for you on Friday. And maybe we'll do another video thing tomorrow, possibly. Let me check the schedule on that. All right. Talk to you guys later.